So now we want to do some review for bonding. And so all of that starts by considering our atomic structure. Recalling, of course, that atoms are made up of a nucleus at the center where we find the protons and neutrons, and the electrons are in orbitals. Now recall that these electrons, which are in orbitals, that these orbitals are not what we would think of by the word orbit. These orbits are mathematical descriptions of where we're likely to find the electrons. And while we have four primary orbital types, S, P, D, and F, for the purposes of what we do in organic chemistry and what we have to worry about in organic chemistry, we really only have to focus on two of these, and that's S and P. Every once in a while when we have, for example, phosphate groups, which we see a lot biologically in things like ATP, do we have to worry about d orbitals. And then there's pretty much nothing in organic chemistry that deals with any elements where f orbitals are relevant. Now, what do we remember about the types of bonds? So we should recall that there are three main types of bonds: ionic, covalent, and polar covalent. Now, what's the difference? So an ionic bond is typically a metal and nonmetal, whereas either type of covalent bond are between two nonmetals. An ionic bond is when we get a transfer of electrons because the electrons transfer from the metal generally to the nonmetal. We get a cation and an anion, and those two species are attracted to each other. Polar covalent is when we have sharing of electrons, but the sharing isn't equal. And covalent is when we have equal sharing of electrons. How do we know when we have each type of bond? Well, the ionic is usually the easiest to spot because that's most common for when we have a metal and a nonmetal. For covalent versus polar covalent, it usually has to do with the difference in electronegativity. So if we have a difference in electronegativity for the two elements that's less than about 0.3, that's usually going to be covalent. Now sometimes you'll see this number cited as 0.4 or 0.5. It's just somewhere in that range. And for polar covalent, we're looking at a difference in electronegativity for the two elements of between about 0.3 and 1.7. Generally, if it's greater than 1.7, that gets us into the ionic range. Now, that's not to say we don't have polar covalent species where the electronegativity difference is more than 1.7. For example, BF3 has an electronegativity difference of approximately 1.9, but because it's two nonmetals, it ends up as a polar covalent bond. So in organic chemistry, the overwhelming number of important compounds are either covalent, and those we see everywhere. Carbon-carbon bonds are nonpolar, and carbon-hydrogen bonds are nonpolar. And those make up the overwhelming majority of our molecules. But we also see a fair number of polar covalent bonds as well. Carbon-oxygen, carbon-nitrogen, OH, NH, as well as any carbon-halogen bonds. And in fact, it's these polar covalent bonds, as we'll learn over the next few months, that it's polar covalent bonds that account for most organic reactions. All right, now before we go any further with this, we want to make sure that we're still very comfortable with something that we learned in Gen Chem. So you should get out at this point in-class exercise number 1, which deals with Lewis structures. There's 10 examples for you to practice there. So give those a try, and the next video will be solutions to those problems.